Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 02 example 01 part B. Before this part, this is part B, we have covered example 01 part A. So in that part, we have started this example. We cover some parts of this example, like you can see here. We covered these topics. So we have this calculation, as you can see here, and this was the final stage where we have stopped, that we finally calculate the factor dead load, and this was the last slide which I have discussed. I have found out the minimum depth, that is 24 inch, and from deflection criteria I have found out 19 inch. Now in this example, if you see here, we have two cases. So in case 1, what is required from us, we see here in case 1 that we have to find out, this is case 1, minimum depth obtained with maximum steel ratio. Now this means that use the rho max value and find out the D minimum value. Now this is one of the most important question, that how to use the rho value and how we can determine the minimum depth to satisfy the ductility criteria, that rho provided should be greater than rho minimum but should be less than rho max. So how we can satisfy this criteria, and we will use the rho value and find out the D value, even if it violates the ACI minimum depth for deflection control. Right? We have determined that the minimum depth D should be length divided by 16 for a simply supported beam. So they say here that find out the D value using rho max, while don't care about this limitation. So let's do this calculation and find out the value of D minimum by using rho max. If you remember in lecture 01, I don't know the part, but in one of the previous part of lecture 01, we had derived an equation for rho max, that rho max equals to 0.85 beta 1 fc prime divided by fy into 3 by 8. We have derived this equation in previous part. It can be easily derived because we know that rho b value equals to 0.85 beta 1 fc prime divided by fy into epsilon u divided by epsilon u plus epsilon y. Yes, epsilon y. So epsilon t, sorry, this is epsilon t. Now let's say we are assuming here that, let's say our rho b reaches to rho max, and let's say our epsilon t is greater than or equal to 0.005. So by using this limitation and epsilon u equals to 0.003, we know this. So from this we can easily find out that fc prime divided by fy 3 by 8, because here 3, here 3, and here 5, so 3 divided by 5 plus 3 equals to 8. So this is the equation, right? We have already derived this equation in previous parts, so please go there and watch that lecture. So from this equation we can find out the value of rho max. Let's say this is 0.85 beta 1, that is 0.85, because the value of fc prime is less than or equal to 4000 psi, so that why the beta 1 value will be 0.85. So fc prime is 3 while fy is 60 ksi. So and 3 by 8 is constant. Now from this we can easily find the, yes, this is 0.375. So if you use your calculator, you will find the value of rho max, that comes out to be 0.0135. So this is my rho max. Now we have derived an equation, I think so, in part 0302 for the ultimate moment mu. We have derived this equation that P equals to rho BD square into, I have already discussed that I will use this equation for solution of the example, so that's why here I am using that equation, that is 0.59 times rho fy divided by fc prime. Sometimes this 0.59 is written as 1.1 over 1.7. So we know all the values. We know the value of mu, that is we have already found out in part 1a, example 01a. The value of the moment is 352.4, multiplied it with 12 to convert it from feet to inches. We know the value of P, that is 0.9. We are using the rho equals to rho max, right? So that was 0.0135, and the B value is 12 inches. The D value, that is D minimum, we have to derive that value. We have to find out that value, and the fy value is 60 ksi. 1 minus 0.59, and the rho value is 0.0135 times fy, that is 60 ksi, divided by fc prime, that is 3 ksi. So noting this point that this mu is kef inches, so that why, so you have to consistent with units, right? Here I'm using kef inches, here this value is inches, this 60 is in the units of ksi, and here we can see this unit is ksi, and here I have also ksi, so that why this ksi cancel with this ksi, and we will finally find out the value for D. So you have to multiply this value with 12, and we have to shift it, these values and this value to the left side, so this value will be divided by these values, right? And then we will divide these values, we will subtract that value from 1, and we will shift it to the left. So finally from this we got the value for D square. The value will be 574.7, and if we take the root, we will find out 24 inches. Now you can see here this 24 inches is already derived from the D minimum formula, that is mu divided by 0.205 fc prime into B. We have already found out the value from D, that is 24 inch. So you can see, because this value D is based on rho max, and we see that the equation of rho max which we used is based on epsilon t, that is 0.005. So that's why this value d with a close are same value as computed from the minimum, because this equation is also derived on the assumption that epsilon t should be greater than or equal to 0.005. So this is the reason that always if you use epsilon t equals to 0.005, right, we can see here in this equation, if you use this equation, the d minimum and that value must be the same value. So finally, area of steel can be easily determined by just multiplying rho max value with BD, and from this we know the rho max value B is 12 inches, D 24 inches. We will finally got 3.89 square inches by using the rho max. So this is the maximum steel ratio, right? This is the maximum steel. This is the maximum steel, right, which based on rho max, right? This area of steel can be provided by using 3 number 8 bar plus 3 number 7 bar. This will give us an area of steel equals to 4.17 square inches, which is round about 7.2% more than the calculated value 3.89. So always we are select somewhat larger value from the calculated, because we can't find such combination of bars which give us the exact amount of steel as we already calculated. So this is the final value of AS, and we will provide 3 number 8 with 3 number 7 bar, and we can find out we will find out the B minimum or spacing of bar, spacing between bar, which is also a check that either we can adjust this 3 number 8 bar in one layer or in two layer. So let's say here we will use 3 number 8 bar, 3 number 8 bar here and 3 number 7 bar here. So we are using double layer. So spacing between bars can be find out. Let's say we are providing number 3 stirrup to the bars. Right. 3 number 7 bar and 3 number 8 bar. So we are using 3 number 8 bar, 1.5 inch clear side cover to both side, number 3 stirrup. So the final spacing between bars, the width of the beam is 12 inches. So 12 minus, I have already discussed this in previous part. So 2 times of side cover, that is 1.5, minus 2 times stirrup dia, we have number 3 stirrup. We are assuming this stirrup, that let's say we are using number 3 stirrup, so that's why we have this leg and that leg, so that's why it is multiplied by 2. And we have 3 number 8 bar, so the diameter of the 8 bar is 1 square inches, and we have 2 spacing right here, so we have this spacing and this spacing, so that's why we will divide it by 2. Number of spacing means we can find out this spacing, number of spacing, this is n minus 1. So we have number of bars, so we have 3 bars, 1, so that's why we got number of spacing is 2. If you use your calculator, you will find the spacing, that is S comes out to be 2.625 inches, and as this is, so finally we got this is the required spacing in between the bars. Now we will calculate S max value and we will calculate S minimum value. These two values are important, and we will check that whether our S is greater than S minimum and less than S max. This is all about for detailing, right? So we will calculate S max. So this is the equation. We have already discussed this in previous parts. So first of all, we need to find out Fs, and Fs equals to 2/3 of Fy, and 2/3 of Fy, that is 60 KSI steel. So from this we got 40 KSI, which equals to 40,000 PSI. Now we will plug this value in the S max equation, that is 15 times 40 KSI divided by 40 and minus 2.5 into Cc. The Cc is important, as we know that we have here, we can see we have 3 number add bar and we have stirrups right here. This is assume that this is 3/8. So this Cc is the minimum cover, which is from the bottom, either from the bottom or either from the side. So here we will assume same bottom and same side cover, and this cover can be determined by 1.5 plus 3/8, which comes out to be 1.875. This is multiplied with 1.875 clear cover. So from this we will got, let me use my calculator. From this I got 10.312 inches, which is the S max value. Now we will discuss the S minimum value. This is important. Here, if you can see this diagram, here in this diagram, I have already discussed this diagram in previous parts. We can see the vertical distance in two layers, which is called as vertical spacing. Here are the ACI criteria, that this spacing must be equals to 1.3 times of the diameter, section 3.3.2, and section 7.6.2 says this must be equals to 1 inches. So if we assume the aggregate size, let's say the aggregate size, let's say we are using here 1 inch, maximum aggregate size is 1 inch. So in this case, this spacing will be 1.33 inches. And from this we will see, so we will select the vertical spacing will be 1.33 inches, right? Similarly, here you can see this clear spacing must be equals to the following criteria. Section 7.6.1 says that it must be equals to the diameter of the bar, right? It must be equals to the diameter of the bar. Section 7.6.1 says it must be equals to 1 inch. Section 3.2.3.3.2 says this equals to 1.33 the diameter of the coarse aggregate, so which is 1.33. Here the maximum diameter of the bar is number 8, so that why it equals to 1 inch, because 8 divided by 8, so diameter of number 8 equals to 1 inch. And the final criteria says it must be equals to, which is optional, right? This is desirable but not specified. Diameter of vibrator say 2 inches. So this is optional criteria. If you are using vibrator, this is ACI, it is optional, but it's not a mandatory, but it is optional. If it is satisfied, so you have to maintain then this 2 inches. So this is my we will ignore this, right, and from this we will choose this one. So the final one will be 1.3 inches, right? So this is my S minimum, right? This is my S minimum. So the final value of S minimum, the final value of S minimum is 1.33 inches. And we see our S calculated is our S calculated is 2.625. So this means 2.625 inches. So we can see this is my S provided. So S provided is greater than S minimum and less than S max. So that's why we can say the spacing of bars is okay. And the final diagram and the final sectional diagram will be, this is my these are 3 number 7 bar, and here this one and this one, this is 3 number 8 bar, and the spacing between these bars, that is S, which equals to 2.625 inches, which is already okay. The clear cover is 1.5 inch to both sides. To the this cover including the diameter of the stirrup is 1.875 inches, while clear cover is 1.5 inches. And these two bars are our optional bars. Let's say we are using here two number 4 bar, but we are not designing these two bars, right? And the stirrup is also assumed. Let's say this is number 3. This is number 3 at the rate of 12 inch center to center. We are assuming right here. So this is all about my final diagram, and the vertical spacing amongst these two bars, it must be remembered, this is 1.33 inches, or it may be 1 inch, right? So this is all about the final cross section of the beam. And in the next part, which is part number so we have covered part E01A. In this lecture we covered E01b, while the last part will be E01c. So see you in that part. Thank you for watching.